So we got to hear the vision of autonomy from Brian in that excellent presentation. I'd like to talk a little bit about the some of the technology behind autonomous vehicles and that technology of machine learning and deep learning that could be applied even beyond, really getting to the core of what is this fascinating set of breakthroughs that have driven artificial intelligence over the past 2 decades. And deep learning is a set of techniques that use neural networks, is a type of machine learning that has been at the core of those breakthroughs. So all the exciting stuff you hear in the news about AI is deep learning is behind a lot of those breaking news. So if we look at driving now, not from the policy perspective, the high-level vision and societal perspective, but really from the perspective of what it means to see the world and to act in the world. Because when we try to teach robots and artificial intelligence systems to drive, we have to now step back and think, what's actually involved in perceiving the world and acting in this world? And that is from the philosophical to the low-level engineering level is one of the fundamental aspects for our society, for our civilization that's fascinated us for decades and really for centuries, is what does it mean to see? So in order to drive, we have to be able to perceive and understand the world around us, the pedestrians, the vehicles, the road, infer through time, through space, what is around us, to be able to reason about the intent, about how the world will evolve before our eyes so we can plan around it. And that planning is the second part, the action. Once we understand the world, we have to act in the world. We have to control the vehicle moment to moment, but we also have to think forward into the future, generate possible trajectories through that world, different plans, and have ways to evaluate, just like we do in other contexts, evaluate which trajectory, which plan is better based on our different objective functions, based on our moral values, based on the different ways we've previously experienced the world and have learned about which trajectory is best. And there's a dance there. That's the game theoretic dance too, because your actions influence the actions of others. And we have learned to play that dance as human to human. And now when there's AI involved, we have to think about how we teach, how we let AI join the dance between human and machine in a way that's successful. So how do autonomous vehicles see the world? There's several kinds of sensors that feed the technology of deep learning. At the lowest level is radar. The nice thing about radar, it's cheap, it's very robust, it does extremely well in extreme weather, but it's low resolution, not much signal. It's only good for really not hitting things that are hard, right? But that allows it to be a really solid backbone for a safe autonomous vehicle, and it should always be there. Now there is a type of sensor called LiDAR, shooting lasers 360 degrees around the car that's providing a much higher resolution of depth information than radar, and does just as the radar does really well in tough lighting conditions and extreme weather conditions, depending on with some constraints, and it has 360-degree visibility. The downside is it's expensive and does not have nearly as much information as what we are able to see with our human eyes. Us human beings taking in the light that comes into the eye, that's very similar to the camera sensor, which is cameras are, the nice thing about them, they're cheap, a huge amount of information. All the stuff you're looking at me now, looking around, the way we understand the world around us is through our eyes and taking in a very similar kind of information that cameras see. That's why this is a very exciting sensor for systems that learn, for using deep learning, for using machine learning. There is so much information there that's waiting to be unlocked. There's enough information in camera data to be able to drive strictly with camera. That's why it's inspiring and thought-provoking and energizing for the entire artificial intelligence community to use vision sensor for driving. And that's most of the talk today will be based on vision, on visible light. But the downside is you need huge amounts of data in order for deep learning technology, especially in the autonomous driving, where you have to have 99.999, the march of 9% accuracy of the systems. You have to have huge amounts of data, huge amount of edge cases. And the downside is that there is a lot of noise in the sensors. There's a lot of uncertainty. It's not robust to extreme weather conditions. It's not robust to extreme lighting conditions. So you have to be able to deal with that just as us humans do when we look about the world. With these sensors and with the ideas of machines that learn, of deep learning, is the question of two paths, two possible paths to achieve autonomy. So one path is using vision, using cameras. It's prioritizing the camera sensor, using radar and ultrasonic sensors as a backbone, but really prioritizing the rich textual information that comes from camera, and using deep learning, collecting huge amounts of data, huge amount of edge cases that are in driving, and learning from them, continuously learning and improving the system. That's approach one. The really nice aspect there, it's cheap, and it's so most cars today have cameras. Many cars today have cameras looking out. So that's the pro. The cons, as I mentioned, it's not accurate unless you have a huge amounts of data. So it's a flawed system. And it's very difficult to achieve perfection. And as Brian previously has talked about, on the path to perfection is a very dangerous gray area where we don't know the human factor, the human behavior, what that looks like. So achieving perfection is necessary to build a safe system, and how hard is it to achieve with this path, perfection, is totally unknown. It may require a huge amount of data collection. And on the other side, the other path to autonomy that's been successfully demonstrated at a small scale to date is using LiDAR and maps. So using the laser sensors to have extremely robust and high accuracy depth information to be able to not hit objects around you, to maintain safe navigation trajectories through the space, and using map information to localize where I am in the world. The downside is that LiDAR data, to date at least, is very difficult to use for deep learning to learn about the world. It doesn't have enough information to really richly learn about the physics of the world, about the visual characteristics of the world, be able to infer and understand the world around you. So let me talk about deep learning. I think much bigger than driving is the ability of machines to learn. That's been at the core of the excitement of the artificial intelligence community over the past decade, and stretching back to the 40s. The success of neural networks, which is at the core of deep learning. So what is it? Essentially, deep learning is the ability to extract useful patterns from data. Huge amounts of raw data, being able to extract patterns that are useful for different kinds of systems like autonomous vehicles. What is behind deep learning? It's neural networks. It's using neural networks of basic computational, simple computational units, just like the neurons in our brain, interconnected, so huge amounts of neurons that are able to contain little pieces of knowledge. And through the process of optimization, we adjust those pieces of knowledge on those simple computational units in order to learn some rich, multi-resolutional hierarchy of knowledge, just like our brain with the 1+ trillion neurons, synapses operating in our brain. The hard part is asking the right question, cleaning, collecting the data, and really getting to the core of what can be automated in a particular application. And I'll harbor on this more and more, is how difficult is really driving, which aspects can be automated, how solvable is it with this technology. And then there's a lot of exciting progress outside of autonomous driving on the right side of the slide in application of deep learning, from face recognition to general image classification, to speech recognition, text-to-speech, general natural language processing, processing text data, going from text to speech generation, handwriting transcription, machine translation, translating from Swedish to English and back, medical diagnosis, a lot of exciting applications in the healthcare industry, and of course, autonomous driving, digital assistants, Alexa, being able to recognize the voice, be able to infer NLP, NLU, understanding what is actually being said. Just the entire aspect of language modeling has seen a lot of breakthroughs, especially in the previous year in 2018. And in ad and search and recommender systems from Netflix to Google, the showing advertisements to you, deep learning is feeding a lot of the aspects of personalization. So an algorithm being able to learn enough about you to recommend, to understand you fundamentally, to be able to recommend what it is that you want to see more of. That's extremely powerful for providing an experience, a product that's useful to the individual. And the fun stuff of playing games and so on, some of the stuff you've seen with chess and Go that artificial intelligence system been able to solve. So, you know, I'm a bit of a romantic. So there's a beautiful aspect to artificial intelligence too, because it's been at the core of our of the dreams behind what we as a civilization have sought, which is to understand how the mind works, how to create intelligence. And just to put it in perspective, because I'd like to help understand, and maybe in Q&A we can have more of a discussion of what is deep learning, whatever its capabilities, but what are also its limitations. So here's a visualization of just 3% of the neurons firing in the human brain. So to put into context, most of the state-of-the-art neural networks have about 100 million neurons in them. And, 100 million synapses, so connections, which is about 10,000 times less than our human brain has. So in terms of scale, all the success that we're seeing today is on systems that are much, so 4 orders of magnitude smaller than our brain. And the question is, as we scale them up, do we start to achieve that kind of intelligence? The history of neural networks and deep learning, starting from in the 40s, have gone through some summers and some winters, 2 winters, where the entire community of artificial intelligence and industry has been extremely excited, but then funding dried out. And the same is repeated twice. And we're now in the summer, once again, of excitement, with a lot of breakthroughs starting in 2009 with ImageNet, breakthrough image classification performance on a state-of-the-art large data set from Stanford. GANs, generative adversarial networks, being able to create new visual information, new audio. It's really exciting to be able to, in an unsupervised way, to create information. Deepface, being able to do face recognition at a level that far supersedes the previous performance and makes face recognition actually good enough to be useful for us to be able to unlock the phone with your face and so on. And AlphaGo, things that when I started in artificial intelligence thought to be impossible, which is the game of Go, was finally we're able to create an AI system with reinforcement learning that was able to beat the world champion in a game of Go. And BERT 2018 is the year of natural language processing. All the exciting stuff from OpenAI, from DeepMind, we're able to create language modeling, to be able to generate language, to be able to translate machine translation, to really have a lot of breakthrough performances on working with language and using deep learning to work with language. Now, once you get an understanding of language, the number of applications, from personal assistance to translation to everything, our world is surrounded by language. Having machines that find patterns in languages is extremely powerful. So we're going to be seeing a lot of world-changing applications in the next few years based on these breakthroughs, with BERT as a system at the core of that breakthrough. So what is deep learning? Really simply, it is the ability to find patterns in data that are extremely simple to work with in terms of inferring and understanding the world. So if you look here on the left is our a simple current view of the world where the Earth, not the world, but the solar system, where the planets are orbiting the sun, with the sun at the center of our solar system. It's a much simpler view of the world, allowing us to reason about this world much easier. Now, for most of human history, the view of the world was the Earth is at the center of the solar system. Now, when you're trying to reason about the motion of the planets, when the Earth is at the center of the solar system, mathematically it's a much harder problem. So what deep learning allows us to do without human experts is form representation of the world, whatever the problem is, whether it's autonomous driving or medical diagnosis, form a representation of the world that allows you to simply reason about it in an automated way. But what is it really when we talk about applying it to to real world problems? Deep learning is collecting huge amounts of data, extracting difficult representative cases from that data, having humans annotate what's going on in that data, and learning from those annotations, and repeating the process. Once the model is trained, you set it out into the world, see how well it performs, and in the cases where it fails, you're now collecting more data of those types of cases, extracting more edge cases, doing more annotation, and then learning once again and improving the performance. And this cycle is at the core of all the applications of deep learning today. It means collecting huge amounts of data, extracting edge cases, annotating them, seeing where the system fails, and repeating the cycle over and over. The power of deep learning versus traditional classical machine learning methods and artificial intelligence methods is that it's able to do the step of feature extraction in an automated way. So answering the question of what are the interesting features about this data that will be useful to solve my problem, it does that automatically. So it removes the human from that part, the expert from that part. And that's extremely powerful because you can now scale the amount of data you can learn from, because the feature extraction is automated. As opposed to having 5, 10, 20 features, you can have millions of features to learn from that are automatically discovered. And that means that you can never run out of data. The more data is better. It always improves with data. Now, that's the power, the excitement of it. Means that with that step, the cycle of force, huge data collection, edge case extraction, annotation, and training, and repeating that cycle, you can solve so many problems in this world. So many aspects can be automated to create products that create great experiences and make for a better world, better lives, better quality of life, and hopefully save lives in the autonomous vehicle space. But there's challenges, and I'd like to talk about them. We're now at this peak of excitement, I would say, on the Gartner hype cycle of deep learning and self-driving. We don't know really where the wall is. We haven't really hit the limits of these technologies, but there are limits. If we look at the systems that are successfully operating in the physical world today, so robotic systems, they're primarily not learning-based systems. They have strong sensors and use rule-based, model-based, optimization-based control to be able to navigate this world. So if you look at Boston Dynamics, really the state-of-the-art robotic systems today, they use almost no machine learning, almost no deep learning. If you look at the state-of-the-art fully autonomous vehicles with a safety driver operating on roads today, they are using almost no deep learning. They're using some deep learning for the computer vision aspect of perception to give fine-grained information on top of what the traditional model-based methods are doing. But at the core, there's no deep learning. Why? Because we're still not able to create robust, reliable, explainable systems with deep learning. Then there's the question of unintended consequences. With a deep learning system, you have to specify an objective function that you're trying to optimize, and you're using data to learn how to optimize that objective function. So on the left here is a simple game of coast runners where the task is to race a boat around a track and to finish. And what's shown on the left is a human player, human being playing this game. The reward structure is the following. You get points by finishing fast and relative to your competitors, the position you finish. But there's a third point as well, sources of points, which is picking up those little green turbos along the way. Now, when you teach an AI system to play this game, as opposed to finishing the race, it learns that finishing the race is actually detrimental to getting more reward. So when the objective function is maximizing the reward, what it learns is to go around in circles, slamming in the wall with fire everywhere, and collecting the green turbos over and over. So that's an unintended consequences of a very simple objective function that says I want to maximize rewards. And at the core of any machine learning system, without a human in the loop, there's going to be an objective function that specifies what's good, what's bad. Now, we human experts are not good at being able to completely define what does it mean to be good. There's a lot of fuzziness, a lot of gray area that we navigate together. But when we have to put it down, an objective function, actually on paper and say what's good, what's bad, there's going to be, when the system runs away with it and operates based on that objective function, there will be unintended consequences, especially in the autonomous vehicle space, that we don't know how to work with. And there's the general problems of pure perception, which is the lighting variations. We take for granted how good our brains, how our visual cortex is with understanding that, for example, the man on the top left is the same person, even though the lighting variation, the extreme lighting variations, different light sources. To a computer vision system, it's a very different, each one of those pictures is very different. All the different pose variations we have to deal with, all the different interclass and interclass variation. So we have to deal with, we have to learn with occlusions. So being able to recognize objects with only part of it is visible. Then there is, and that's the pure perception. Then there is the much bigger problem of just even understanding the scene. Here's a picture of former President Obama making a practical joke on one of the staffers stepping on the weight. We don't know how to reason about the reflections in the scene, which is extremely important for autonomous vehicles. That the person in the mirror is not a real person. We don't know how to use extremely sparse information. Like most of us are able to recognize that it's a President Obama from just a few pixels of his face. We don't know how to do 3D structure except minimally through motion from the scene, and us humans are able to immediately infer that there's a foot being stepped down onto the scale. The physics of the scene, the gravity, we don't know how to reason about in deep learning systems. And the big one for autonomous vehicles is being able to infer what's on people's minds, the mental model of what's going on in the scene. So be able to reason about what another person is thinking about and what that person is thinking about another person thinking about. And that kind of chain of reasoning that we do when we infer, for example, how to navigate an intersection with pedestrians. The other challenge demonstrated very powerfully in a new field of adversarial machine learning, simply here on the left, a 99.6 accuracy prediction is made, confidence prediction is being made that the image on the left contains a dog. Adding a little bit of distortion to the state-of-the-art network makes it predict with 99% accuracy that that's in fact an ostrich. So with a little bit of noise, we can manipulate what the system sees. So it's not robust, these specific adversarial examples. And the other big one is the efficiency of learning and the generality of learning. So we as human beings, here's a baby learning to walk or walking for the first time. We're able to, from just very few examples, this is the first time this baby has been on 2 feet, right, with unassisted. You're able to learn a huge amount of information from just a few examples. That for current deep learning, machine learning approaches, we need tens of thousands, hundreds of thousands, millions of examples even to learn trivial things. Walking, as we'll see, is non-trivial, is extremely difficult, and we're able to learn from just a few examples. So where do we stand in the autonomous vehicle space? Waymo, in the two paths that I've mentioned, of full autonomy and partial autonomy, of using deep learning, computer vision, and vision camera sensors, and using LiDAR. Waymo is the leader of the space of full autonomy. They've achieved, in 2018, 10 million miles, and now it's going up. Tesla, on the computer vision, deep learning side, has achieved now over 1.3 billion miles driven under Autopilot. And the question in everybody's mind thinking forward with this technology is, what is going to be the successful path? Who is going to be the company? What set of ideas will be the ones that achieve at scale deployment of autonomous vehicles? And the fundamental question you need to ask is, who's the first to achieve full autonomy with some significant scale, like 10,000 vehicles? And I've often asked people of this question, and there's a lot of debate, but the two leaders are Waymo and Tesla. But whatever the approach is, whichever is the right approach, the answer will not, autonomy will not be adopted, in my view, because it makes us safer, or because it gets us from point A to point B faster, or because it's cheaper than the current transportation system. It'll be adopted because it creates a better experience. And I think that's the fundamental thing that we need to solve. On the deep learning side, the algorithms we employ need to be ones that create a better experience. And our intuition about the state of autonomous vehicles that I think is misleading, that takes us away from creating a human experience, that takes us away from creating a human-centered autonomy, is the following. One, that was grounded, as Brian described the history of autonomous vehicles, grounded in the success of the DARPA challenges, where cars successfully drove through the desert autonomously, and then a few years later successfully drove through a city, through an artificially constructed city environment autonomously. They give us false hope about how easy this problem is. And I would summarize the intuition in 3 points. One, we believe the driving task is easy. That you just stay in lane, stop for a stop sign, stop for a red light, go when it's green, and so on. It's easy to automate. Step two, or assumption two, is that humans are bad at driving. There's a lot of examples that we saw, people doing all kinds of things in the car, or constantly distracted, drugged, drunk driving, and so on. So if driving task is easy and humans are bad at driving, it'll be easy to automate the task such that it'll be safer than a human. Those are the two assumptions. And finally, the third assumption is that humans and automation don't mix well. There's a lot of body of literature where the interplay is very difficult to get right, the collaboration between humans and machines. There's a lot of work that's showing that humans will become complacent, will become disengaged, will overtrust the system, and so on. Those are the assumptions that led to the development, that led the big push towards full autonomy, of creating LiDAR-based systems that are, essentially don't have a steering wheel. But while those assumptions may hold true, it is my belief that they will not. And we have to think about how we engineer systems when they don't hold. That all those assumptions are wrong. And let's look at them a little bit more carefully. Because if the driving task is easy, we have to solve this problem of nonverbal communication between cars, the subtle and not so subtle dance between vehicles when we change lanes, when we interact with each other in intersections. We have to react in split seconds, 100 milliseconds, 200 milliseconds in extreme lighting conditions. When the visibility is extremely difficult because the lane markings are blocked, the different characteristics of the roads are blocked because of snow or rain, and the slippery nature of the road makes it difficult to make controlled decisions in a timely fashion. And the most difficult aspect is the humans, always, is the pedestrians here, or the cyclists. We have to be able to navigate through this intersection. We have to assert our presence to this intersection. So you'll see here a few vehicles pushing themselves through, nudging themselves through. At, in terms of robotics, in terms of computer science, computer vision, path planning, we don't know how to design algorithms that assert themselves, that threaten pedestrians essentially with their movement, or take a risk in order to make the pedestrian not cross. That game theoretic dance we don't know how to reason about. And we have to solve it if we want to solve the driving task. And of course, the thing I already mentioned is the unintended consequences. So when you specify through that intersection an objective function that needs to be optimized, what are the unintended consequences when we task the autonomous vehicle to nudge itself through a group of pedestrians? It's very difficult to anticipate them, but it's possible that they arise. The idea that humans are bad at driving, I think in general we make assumptions about our visual systems because we've had it for 500 million years. We take for granted how difficult it is to see and perceive and understand the world. We take it for granted how difficult it is to do bipedal movement of walking on 2 feet because we've been doing it for 200 million years. And we tend to over-exaggerate how meaningful thought and reason is, which is why we give a lot of credit to chess as a difficult problem, because we've only had it recently as human beings. But in fact, bipedal movement and visual perception is extremely difficult. Here on top is the state-of-the-art human being performing those tasks, and on bottom is the state-of-the-art robot performing those tasks. We take for granted how difficult it is to walk, to run, to respond to uncertain conditions, and how to, under those uncertain conditions, execute successfully. The same is true with just even basic movement. I showed the baby walking for the first time, perhaps much more successfully than the state-of-the-art multi-million-dollar robots and below. So the state-of-the-art human, but we can even just go back to the baby compared to the state-of-the-art robots. So these are semi-autonomous robots where there's still humans helping them navigate, but under imperfect communication channels. So they're not even fully autonomous, and they struggle with the basic task of walking, opening a door, of stepping down and up a step, and so on. And the idea that humans and automation don't mix well. I think Brian spoke eloquently to this point, so I won't talk too much about it, but it's an open question. There's a lot of body of literature, and in the work we're doing here at MIT, collecting the data in these different types of systems, that there is a lot of evidence and a lot of open questions about what happens when the systems get better and better and better, and we begin to overtrust and become complacent. But there's also a hope, as was mentioned in the Tesla data that we've collected. There is elements that seem to manage successfully the natural tendency of human beings to overtrust, to become complacent, to lose vigilance. In our data set, in the 18,000 moments when the driver chooses to disengage, they seem to be remaining functionally vigilant. So there's elements there that are working. This dance between human and machines are working. We need to be able to specify, make explicit what is it about that works. Is it the, as Brian talked about, the imperfection of the system? So when it fails every 9.2 miles, is that an essential element? Or is it the another essential element, the ODD, operational design domain, being not very restricted? So drivers of Tesla vehicles being allowed to essentially use the system anywhere on the road, and through the experiential learning be able to understand the limitations of the system, and really that they can't trust the system to drive itself autonomously, that they need to always be paying attention. So this approach of human-centered autonomy means that on the path, if those three assumptions don't hold, and in fact the driving task is hard, and the humans are actually very good at driving, and it is possible to design systems in a human-centered way that manage that successfully collaborate between human and machine, then that means that some high percentage of the time, 90, 95, even 99% of the time, the system is able to perceive the world around itself and plan successfully. But when it fails, when it doesn't know what to do, the human is there to catch it. But at the core of how we solve that problem is data. And there's two camps. There's two ideas of what is the main most promising source of data based on which we can learn to build autonomous vehicles. So one is real world data. And that means collecting data from manually driven vehicles, the 3.2 trillion miles driven every year, semi-autonomous vehicles like the 1.3 billion driven in Tesla Autopilot, or the fully autonomous vehicles being tested on public roads, the 10 plus million miles driven in Waymo vehicles. The other side is simulation. So being able to simulate the miles driven, so the billion, trillion miles, and then solve one of the two problems that connect simulation to the real world. So one in machine learning is the problem of transfer. It's called transfer learning, which is basically being able to successfully take knowledge learned in the simulator, which is different from the real world, and successfully apply it to the real world. That's an unsolved problem currently. The other approach, which is taken by NVIDIA and people working in graphics, is to create a hyper-realistic simulation, that there's essentially no difference between the simulation and the real world, so that everything you learn in simulation is in fact going to be applicable to the real world. And the other approach is to say, well, as opposed to trying to create a perfect system on these large sources of data, is you deploy an imperfect system and you learn, you improve continuously. But then it requires solving the human-centered problem of managing, of collaborating, of perceiving what the human is doing. And one of the exciting projects that we've been doing with Veoneer is taking on this problem. We have a semi-autonomous vehicle here, testbed, that we've been working on at MIT that explores some of these ideas. Here, just to show you a few clips. Here, myself.
Lex, you appear distracted. Would you like me to take over?
Tweeting here.
Yes, please.
With a smartphone.
Great. I am taking control of steering and braking.
Using voice to communicate the exchange
The
of control.
Is now in control, as the center stack display shows. So I will continue with the tweet.
Glance classification of whether the driver is looking on-road or off-road, allowing one to engage in the most important task of the day, which is tweeting. Here is an illustration
Elevated
of pedestrian
driving risk detected.
and risk
I am
estimation.
stopping for a pedestrian.
So estimating the risk of the environment based on the presence of the pedestrian and other factors. So here slows for the pedestrian.
Lex, pedestrian is blocking our lane of travel. Should I honk?
No, please shift.
And so there's in the human-centered approach, there's a set of fundamental open problems that need to be solved, and we're taking on each of them. And I'll show you a few clips of the first one. But first, it starts at driver sensing, being able to perceive what the driver is doing, perceive everything about the human being, from where they're looking to the cognitive load to the activity. Then there is interacting with the pedestrians, with the humans outside the vehicle, and getting right that game theoretic dance between getting from point A to point B fast and doing it so safely. And then there is the managing of the functional vigilance, the creating systems where the human don't become complacent, don't overtrust, and really importantly, creating an enjoyable, valuable experience where people would want to use the system and want to pay for the system. And the social factors of public perception and policy, of course, are extremely difficult and extremely important to solve. So to give you a sense of much of the focus of our deep learning work on the driver side of perception, there's so many interesting things that could be detected from the raw of pixel data of the driver. So it's starting from just the basic detection of body pose and classifying where the driver is looking, to the more interesting, subtle things about the movement of the pupil, the cognitive load, drowsiness, and so on. So it starts with glance classification, determining when the driver is looking on-road or off-road. It also includes emotion recognition. Here is driver frustration detection, detecting in a binary classification task of whether the driver is content, happy, or dissatisfied, frustrated with an experience of using voice-based interaction with a navigation system, a source of a lot of frustration for people. And I think the reason this is a really good example of what the power of deep learning and the power of data is, as opposed to engineering a system from human experts, we let the data speak. One of the things that we discover here is one of the strongest features of frustrated drivers that appears over and over is a smile. So a smile is an indication of a frustrated driver. Now, this is different than you would think in a traditional affective computing context, where a smile is almost always indicative of a happy person. And that's really important because you essentially let the data allow you to discover the features that are important for this particular application. A really important source signal of information for the state of the driver is the eye, and in general the pupil. So blink and pupil position gives a lot of useful information for cognitive load and for drowsiness. Here we have a state-of-the-art detector of blink and pupil. Here counting being able to detect accurately the blinks and saccadic movements when the person is looking around. And finally, for smooth pursuit, being able to accurately, temporally smooth over time the movement of the eye when it's subtly tracking a object across the scene. So that information, as I mentioned, can now, the raw pupil position and the blink can be used for drowsiness detection, or as in this case, used for cognitive load estimation. So determining how overloaded mentally the driver is, how deep in thought they are. So even if they're looking on road, they may not be actually fully engaged with the road, and their mind wanders. Mind could be elsewhere. Then there is the activity, looking at the body of the driver. So here, there's three categories: a driver not using a smartphone, a driver having a smartphone in their hand but looking at the road, which is yellow, and green is when the driver is looking at the phone. So the ability to use deep learning to determine when the driver is engaged in a particular activity. Some activities might be conducive to good, safe driving. Some may not be. And that information could be extremely useful for a car to have. So in the meantime, there's just an exciting set of progress, but also a difficult set of challenges that we need to solve. We need to collect huge amounts of data, applying machine learning methods to learn from that data continuously through that cycle, through the edge cases, improving and improving the system. And finally, as we deploy these systems, being able to solve all the human-centered autonomy aspects, where from sensing the driver to managing the complacency and all the difficult societal issues. And I think that's really exciting for the artificial intelligence community, because we get to graduate from the successes of the past decade, which were essentially on toy data sets in image classification, looking really at the difference between a cat and a dog, performing state-of-the-art there, but not much use in the real world, not impacting the lives of people, and get to graduate to use these same algorithms of neural networks to build autonomous vehicles, to do medical diagnosis, and so on. It's a really exciting opportunity. At the core of this opportunity is always a question here from one of my favorite Swedes, Max Tegmark, who's now at MIT, visualization of the rising sea of human competence is basically different problems in the space. You can think of different applications in the space, and as our artificial intelligence systems, as the power of deep learning grows and is able to solve many of these problems, the questions arise of how difficult various problems are. So in this visualization, we're just about, our best techniques are just about to solve driving. So driving is very close to sea level. It's still an open question how difficult that case is. But we also have to think about scientific of natural language generation, of theory improving, and all the different jobs that could be automated, how difficult they are. And that's extremely exciting to see where the big impact in the near future could be. And of course, in the long term, the question is, how do we create a general intelligence? And by that, I mean systems that are able to not just solve autonomous driving, but learn how to transfer knowledge from one domain to another, just like us humans do, just like that baby is able to elegantly do with just a single or just a few examples there, walking for the first time. So with that, I'd like to thank you for being here, and thank you for being here in Sweden. It's my first time here.